Okay, you should be able to see my presentation now.
Yeah, we do.
Okay, yeah, so I will be presenting a combinatorics problem of this year's final round. And officially it comes from Austria. There they used it in 2016. So we can start with the problem statement first. So we are given an n times n chessboard where n has to be at least 2. For example, here n equals 4, we just have a normal chessboard. And then k stones are placed on that chessboard on any of the fields. So yeah, the numbers in each field represent how many stones are in that field. So in this example, k is 14. And we're kind of playing a game, and a move in the game is that we pick a square that has enough stones, which means that it has as many stones as it has as neighbors, and we give 1 stone to each neighbor. Now, neighbors have to share a horizontal or a vertical border, so they can't just share a corner. That's not enough to be a neighbor. If you look at the squares, only the 2 that are marked now have enough stones to make a move. Some of them have 0, of course they can't make a move. The top corner only has 1 stone, but it has 2 neighbors. And then there's another square that has 3 stones but 4 neighbors. So we can only make moves with those. Yeah, so for example, we can make a move with the square that has 7 stones, just to show how it works. So we just give 1 stone to each neighbor. Then it has 4 stones. So we can make another move because it has only 3 neighbors. Yeah, then we can make a move with the square that has 3 stones. And then a last move with the square that has 2 stones at the bottom left corner. And now we can't make any moves anymore because none of the squares has enough stones for each neighbor. So those are the rules of the game. And now we will come to the actual problem statement. So we are asked for which k there exists an initial configuration. So note that it doesn't have to mean that each configuration with k stones has these properties, where in part A, no move is possible. So for example, if we have n equals 4 and k equals 14, the table that we have here right now is an example where no move is possible. So k equals 14 would be a valid answer for n equals 4. And also maybe another example would be, well, each square has at least 2 neighbors. So if every square has exactly 1 stone, there are no moves possible. So again, just another example to illustrate part A. And then there's also part B to the problem, where there is an infinite sequence of moves. And for this, we can make maybe a simple example, which is we give every square 100 stones, and then at least one of those squares will have at least 100 stones at any point, no matter how it's moved, just because there are that many stones by the pigeonhole principle. Yeah, so that means clearly at least one square will have as many stones as it has neighbors, so you can just make an infinite sequence of moves with that. Yeah, so now we will proceed to find all the k that satisfy these properties. We can start with part A, where we are trying to find all the k's that have a configuration where there are no moves possible. Now, after playing around for a bit, you may want to try to fill up each square as much as you can. So in particular, you do this, which means you give each square the number of neighbors that it has -1 stones, because then it's filled up to the maximum basically, and adding 1 more stone would give it a move. And this will lead to the bound 3n squared minus 4n, which can be counted, but I'm not going to do that now. And yeah, again, to prove that all smaller k, okay, up to that bound work, well, we can just distribute it the way that it is shown in this picture. And if k is lower than that number, we can just take away some stones from any square we want in this configuration and it will still work. And now we have to show that it doesn't work for any k larger than this. And again, we can use the pigeonhole principle. So if we add one more stone to this configuration, then no matter how the stones are distributed, at least one of those squares will have at least one stone more than it has right now, which means that at least one of the squares will have as many stones as it has neighbors, and it could make a move. So here we have the exact bound is k is less than or equal to 3n squared minus 4n for part A. Now we come to the bit more difficult part B. And first of all, we can find a relatively easy bound. Again, just to repeat, we are looking for k where we can make an infinite sequence of moves. A relatively easy lower bound is just to take everything that's larger than what we had in part A. Because no matter the configuration, we could make a move in the beginning because, well, at least one square had one more than in that table I showed. But after one move, or after any number of moves, the number of stones doesn't change. So the same argument applies, and there's always going to be at least one square that has enough stones for each neighbor. So from part A, we can basically borrow this bound. But now the question is this the best possible bound? And it would be kind of weird if it was, not because it's the same bound as in part A, maybe that just happens in some problems, but because in this bound, the configuration doesn't matter. No matter how you distribute the squares, it always works with that. And that seems like we're kind of wasting stones. So we have to look if there might not be a lower bound. And after trying around for a bit, you might come up with this idea that you make the chessboard pattern out of the chessboard. So again, here we have our example with the 4x4 chessboard. And we fill all the black squares. And what I mean by fill is we give each of the black squares as many stones as it has neighbors. Then by definition, we can make a move with each black squares because we've given it exactly as many stones as it needs for a move. So what we do is we make a move with all of the black squares in any order. And what happens now is this. So now we have a lot of stones on the white squares. And if we look at the numbers, each square has exactly as many as it needs for a move. Now, is this a coincidence? Well, no, it's not, because each white square has received exactly one stone from each of its black neighbors. So by definition, it will have exactly one stone for each neighbor. So it has enough stones to move. So now we can just keep repeating this move. So we will now make a move with each white square, and we will get back to the configuration we had in the beginning. And then you can make a move with all black squares and just continue like that. So this definitely works. And again, I'm not going to count it here, but you could count it pretty easily that the bound is 2n squared minus 2n. And that number clearly works. Any larger k will also work because you can choose your configuration. So what you can do is you just ignore any other stones that are on there, and you just keep repeating this pattern that we've done so far. So all larger k will work. But now again, we have the question, is this the best possible bound? And if we want to show that it is the best possible bound, we not only have to show that it works for 2n squared minus 2n and all larger k, but we also have to show that it doesn't work for any smaller k. And yeah, for that, we are trying to prove the sharpness of the bound. So again, here is our equation that we are trying to prove. And now, yeah, so this was an exam, the problem was in an exam for which we had, I'm not even sure if it was about 4 hours, I think. And I spent 2 hours on this next step. And then after a while, and after trying out many examples, I came up with the following claim, which is not very trivial. And it is that we need at least one stone per internal border. And in the end, there are exactly that many borders. And of course, we now have to prove this claim and not just claim it because the number seems to be close.
Sorry, internal border, you mean the edge between the two squares?
So can you see my mouse?
So what is the internal border and edge between two squares?
Yeah. Can you see my mouse? So it's just this.
And internal, this means it doesn't touch the outer boundary.
Yeah, so it's not one of these.
Oh, but what about like between the upper right corner and black 3?
Yeah, this is this one. So it's just the internal one. So these.
Mm-hmm.
Yeah.
Okay.
So like if you take away the outer border of the square, then all the grid lines basically. And so just the lines between two adjacent squares, not lines that go to the outside. And if you count those, that's exactly the number that we are trying to prove. So now we still have to prove this claim. And for that, we will start with a lemma, which is just an easier thing to prove. And what this states is that in infinitely many moves, each square has to be chosen infinitely many times. So basically, for example, if we take the upper left square, it's not possible that it's done after 100 moves. Each square will have infinitely many moves. And how do we prove this? Well, we will look at two neighboring squares. Well, clearly in our chessboard, there will be at least one square that has infinitely many moves, just because there are infinitely many moves in total. So if there is at least one square that only has a finite number of moves, there will also be at least one square that has a finite number of moves and is adjacent to a square that has an infinite number of moves. But now, here we run into a contradiction because let's say the square marked with an X, if that square has had its last move, the square on its right with the infinitely many moves still has infinitely many moves left. But then at each move, it gives one of its stones to the square on the left, and the square on the left doesn't make any moves anymore. So after k moves of the square with infinitely many stones, with infinitely many moves, the square on the left that only has finitely many moves already has all the k stones, but then all stones would be on that square, and then no more moves would be possible, so there won't be an infinite sequence anymore. This means that there cannot be a square that is chosen only finitely many times. So we have proved this lemma, and now we will go on to prove that claim. And for that, we will need an injection from the borders to the stones. Now, again, we are only looking at the internal borders between two squares. And how will we construct this injection? Well, to each border, we assign the first stone that crosses that border. So here we have our example. Let's say we have a lot of other stones, but we're not showing them here. But we have this one stone on that left marked square, and it moves over the border, over to the right square, and it's the first stone to go over this border. Then this border and the stone are assigned to each other. And now, on every move where that stone can move over that border, it will always move over that border. So we will always have this happening. And because of lemma 1, we know that each square has at least one move, which means that each border is crossed at least once. So every border will have its first stone. But now, what if the stone goes to one of those squares with a question mark and is also the first stone to cross the borders there? Because then it would not be an injection anymore, because multiple borders would have the same stone. Well, this doesn't happen because we've said every time it can move over this border, it will keep moving over that border. And whenever the stone is on that square and it is forced to make a move, one stone from that square will go to the left. So we can always pick this stone to go to the left in that case, so it will never be forced to go to a question mark. Again, just to repeat, from that square, exactly one stone will go to the left on each move, so we just pick the stone that's assigned to that border to go over that border. So what we can conclude is that as soon as a stone is assigned to a border, it can only cross that border. So we will have an injection. And if we have an injection, that means that there will be at least one stone per border. So we've also proved our claim, which now means we are done, because we've proved that for all k greater than or equal to 2n squared minus 2n, it works. And because we need at least that many stones, no lower number will work. So now we'll go to just quickly recap. 2n squared minus 2n is the number of borders that we have. 3n squared minus 4n, that was the number of neighbors of all the squares in total, minus the number of squares, so that we can give each square the number of neighbors that it has of stones, and then minus 1 for each square. And here I'm going to show you a table where we have the different values of k and the different options, whether there are no moves, whether there are some moves, and whether there is an infinite sequence of moves. So what we can note here is that between 2n squared minus 2n and 3n squared minus 4n, depending on the configuration that we have, it is possible that there are no moves at all, some moves, or an infinite sequence of moves. And also we can see that for a k smaller than 2, there are no moves no matter how they're distributed. And for k greater than 3n squared minus 4n, there's always an infinite sequence of moves, no matter how the stones are distributed. Yeah, so this is the problem that was on the test. But after the test, you could think about generalizations, because thinking about it, we didn't really use too many properties of the chessboard. We never really used the way the squares are assigned. We never really use that they have between 2 and 4 neighbors. We only kind of used parts of it. So we will try to generalize this. Because basically what we can do with the square is we can see it as a graph. So for those who don't know what graphs are, we have vertices, the round things that represent the squares of the chessboard. And then we have edges, which are the lines connecting the vertices. And each of these lines represents a border. But we could generalize this for all graphs, so for all kinds of connections between those kinds of points, and they don't have to be arranged in this special shape. So we will look at this now. So we will have a graph that is given with some set of vertices, which are those round points, and a set of edges, which are the connections between them. And we only look at connected simple graphs, which means that like you can reach each vertex from each other vertex using the edges. And a simple graph just means that, for example, there are no 2 edges between 2 points, or that there isn't an edge that goes back to a point itself. And it doesn't have to be connected and simple, but there are just some ugly special cases that we are not going to treat right now. So for part A, again, we are looking for K where there exists a configuration where there are no moves possible from the beginning. K has to be smaller than or equal to twice the number of edges minus the number of vertices. Because in a graph, twice the number of edges is exactly the sum of the number of all neighbors. And then minus the number of vertices, because each vertex has its number of neighbors minus 1. And we can use the exact same argument from before to just say, well, because each vertex has fewer stones than it has neighbors, it can't make a move from the beginning. And again, if we add 1 stone, then at least one of the vertices will have too many stones. So there will be a move possible. So that's why that bound is correct. Now we go to part B, and we claim that it works for all K, which are greater than or equal to the number of edges, which is the equivalent of what we had basically, because before it was the number of borders, the 2n squared minus 2n. And now we just take some graph and we want it to be greater than or equal to the number of edges. And now if we look at the sharpness of the bound, the proof is the exact same as before, the thing with the long complicated claim from before, because the only property we really used of the graph before was that the graph was connected, so that we have the thing with the neighbor of ring squares where one has infinitely many moves and the other one has finitely many moves. But other than that, we didn't really use any properties of the chessboard, so that works. However, the lower bound, the construction that we had with our black and white squares, doesn't work anymore, because that's a special property of bipartite graphs, which doesn't apply to every graph. You can't just color every graph black and white and have these properties that we had before. So we will have to find a new construction. And this is what we are going to do now. So again, just to remind ourselves of the bound that we are trying to prove. So let's say this is our graph. Again, a graph is just a connection of a number of vertices and some connections between them, the edges. And what we do with this graph is we arrange the vertices in such a way that each of them is at a different height. And then we want to prove that it works for K greater than or equal to the number of edges. So what we can do is we can really assign 1 stone to each edge. And now we want stones to start on the vertices. So we will just always pick the lower vertex and put the stone there. So you can see this now. And now we can count how many stones each vertex has. And we can see that we can make a move with the lowest vertex. And that is because it has exactly 2 neighbors, as you can see, because it has 2 edges, and it has 2 stones going to it. Now, is this a coincidence that we can make a move with the lowest vertex from the beginning? It's not, because every vertex gets 1 stone for each edge that goes upwards from the beginning. And for the lowest vertex, all edges go upwards. So it will have, for each neighbor, it will have a stone from the beginning. Now we can make a move with the lowest vertex. And then this happens. And this will always keep repeating. Now, each vertex has a stone for each of its higher neighbors, just from the beginning, because we put the stone always to the lower vertex. And it also has a stone for each of its lower neighbors, because the lower neighbors have already made their move and given 1 stone to each of their neighbors. So we can keep repeating that, and this will keep working, and we always will have that 1 vertex that can make a move until we get to the top vertex. And again, all of its neighbors are lower and they have made a move already. So the top vertex will have enough stones to make a move. And then each vertex will have made a move. And if each vertex makes a move in that order, the way we've shown it here, it will mean that each stone will have started at the bottom of its edge. Then it will have gone up the edge to the upper vertex. And then from the upper vertex, it will have gone down again. So it means that we are again at the beginning on the first graph on the very left that we have. So we can just keep repeating these moves indefinitely. So again, we have an infinite sequence of moves. We have proof that it doesn't work for lower numbers because of the proof that we had from part B. And for all larger k, it obviously works because we can just put a stone somewhere and just ignore it, and we can still make infinitely many moves. So this means that here we have the exact same bound. So again, to summarize, we can say that basically the same bounds that we had before. Of course, they're not depending on n, but on properties of the graphs now, because we don't have any n in these graphs. But we can say that the same bounds that we had in the problem also work for general graphs. Yeah, and I'm done.
Okay, thanks a lot.
Thank you.